Hello all, welcome to my course on methods of adhesion measurement theory and practice. We are at lecture 60 today and we are discussing about adhesion on a rough adhesive, and the rough surface has to be characterized, and that is what we started doing in the last lecture, and we are discussing this topic mainly from this paper and several others by Professor Patterson and a few others. So, we discussed in the last lecture that the surfaces have this self-affine fractal structure, and that can be described by this definition, that if you magnify the surface, then the profile remains, that magnified surface profile remains exactly same as the original image if you multiply it by this quantity magnification index or magnification to the power this quantity h. H is the Hurst exponent. When h is 1, then we have self similar surface, otherwise we have got self affine fractal surface. So, what do we do with this? So, we obtain what we can obtain is known as this pair correlation functions. So, that shows that how the surface patterns they keeps on coming with some interval or like that. So, this is obtained by this quantity h of x into h0, and this sign means it is ensemble average. So, several such multiplications, that means the multiplications are taken and then you obtain the ensemble average of that. So, that is called this pair correlation function, and what is done is we obtain the Fourier transform of this pair correlation functions, and this is in 2 dimension. It is represented by this quantity, and what you obtain in Fourier transform is the amplitude or basically the power of different wave vectors. So, the wave vectors has the wavelength, this q as you might imagine, this is 2 pi by lambda. So, lambda is the wavelength. So, in essence what we are doing is that this surface is being dissected or being divided into all these different wave vectors or wavelengths, and their contribution to the total or the total profile that is being estimated. So, this particular term is called the power spectrum CQ, and it so happens that when you plot this CQ as a function of Q, you obtain this kind of power law dependence. So, there will be some constant into some power law dependence, and this power law dependence written something like this, q to the power minus of 2 Hurst exponent plus 1. So, I have told in the last lecture what is this Hurst exponent. So, similarly, so I just wanted to show you one example. So, here for example, there is a surface of which is obtained which is examined by different methods. For example, this is the optical profilometry of a surface, this is the atomic force microscope images. So, optical profilometry has got this spatial length scale from 0 to 800 micron, that is quite macroscopic, although the height variation is from minus 3.4 to plus 3.4 micron, and then you take a small part of this surface and magnify it by using this atomic force microscopy, and now you examine it within this dimension 50 by 50 micron, and you will have this kind of surface feature, and then you further magnify it, take another small part of it, and then you do the atomic force microscopy. Let us say now it is 0 to 1.6 micron. So, it is 1.6 by 1.6 micron area, and you scan it, you will have this kind of roughness, and you may take even smaller area and then further magnify it, further image it, scan it, you will have again another roughness, so like that. So, these are the different profiles that you can get, and in all case you obtain that power spectral density by this relation, and this is basically Fourier transform. Now, what you obtain is something like this. So, this different color signifies different range, different scan range. So, different scan area that this scan has been done, and then all the scans, and then the number of times these scans have to be done in any given area, in scan area, you average it out and then you plot all these scan ranges, okay, all these different ranges of scan, and see green is one range, red is one range, black is one, and like that. And you can see that all this data fall on a single line when you plot it with respect to log scale. Okay. So, when you plot it with respect to log scale the data, and you can obtain this relation between this power spectral density with this wave vector, okay, by this kind of relation, where this q to the power minus 3.79 is actually equal to like this minus 3.79, and from there you can calculate what will be h, and then you can calculate what is the fractal dimension, that is d is equal to 3 minus h. So, that is the way we can characterize this surface. So, here for example, h will come out to be 0.89 or so, and therefore, the fractal dimension is about 2.105 or 2.11 or like that. So, once you obtain this fractal dimension and also we obtain this relation, importantly this particular relation, then I will show you that we can obtain lots of information. Now, what happens over here, this relation that you get, that now remains independent of the scan magnification or the scan area, scan size. So, this relation that you get for a particular surface, that now you can apply to all different ranges. So, for example, here this q being large, so q being large means it corresponds to the smallest features. Okay. So, this range, okay, smallest features means since you are using an atomic force microscope, so this range corresponds to the diameter of the atomic force microscope tip. Okay. So, one cannot have the better resolution than the diameter of the AFM tip, right. So, this corresponds to that, and over here this corresponds to the large features. So, that means here the q is small, and the q, as I told you, this is 2 pi by lambda. So, q being small means the lambda is large. So, that means this range, okay, small q corresponds to large wavelength features or large features on the surface. So, over this whole range, okay, you have got one characteristic equation. That is the beauty of this way of characterizing the rough surface, having this power spectral density PSD curve. And once you have this relation, then you can obtain many things, different way you can characterize it. So, here I have already told, so let me come back here. So, here for example, you can obtain the RMS roughness of the surface. So, by RMS roughness to RMS roughness, one can show that this RMS roughness will be given by this particular relation. So, where q1 and q2 are these two wave vectors, two limiting wave vectors, okay, minimum smaller wavelength vector and the larger wavelength vector, something like that. So, q1 to q2 are the two limiting values basically of q, and this HRMS square, okay, that as you can see is this takes into account this is becoming more prominent at the smaller value of q, right, at the smaller value of q. So, that means the large wavelength features. So, this HRMS, okay, that contains the information of large wavelength features, and that becomes important for certain phenomena. For example, hydrodynamic and drag effect. Okay. So, there large wavelength features, so very small wavelength features doesn't make much difference. Flow separation, vortex training. So, all these phenomena in the fluid mechanics where you work in flow is the matter here there, where it is the large wavelength features that becomes important. So, HRMS is good enough for them, and then super hydrophobic effect, that also is affected by the large features. So, therefore, for that HRMS is good to know, and weightability hysteresis. And we can also obtain the gradient, okay, or the slope of the HRMS slope, root mean square slope of the surface by h dash RMS, represented by h dash RMS square. So, here, okay, this is the relation for that. So, one can obtain that. So, since you know this C as a function of Q, we can easily obtain what will be this form, right. And so, here this is the HRMS, H dash RMS. As you can see now from this plot, the also estimates this quantity, estimates the area under this particular curve, and so therefore it considers or it takes into account even smaller features. And the root mean square curvature, when you go to the curvature, okay, there it is the very small scale features that become more dominant. Okay. So h dash RMS, h double dash RMS, that is the root mean square curvature. So that has the information about this very small feature, okay, of the surface. So you see, once you have the PSD curve, then depending on your area of interest or the range of phenomena of interest, if it is a very small scale phenomena, ultra small like nucleation, or let us say friction, adhesion, micro scale deformation, you try to find out, okay, characterize the surface by h double dash RMS. If you want to have intermediate, you do it by h dash RMS. Now h dash RMS is also important for adhesion in the sense that once you calculate this quantity h dash RMS square, you can calculate the actual area. Okay. So nominal area is the A0, the normal nominal area, but then because of the surface having this kind of roughness, the actual area is projected is large. So that can be estimated by calculating this h dash RMS square, for example. So nanoscale weighting, microscale deformation or adhesion, friction, nucleation, okay, those phenomena that gets affected by the small scale features. So therefore, okay, you consider this root mean square curvature for that, and you know that curvature, okay, is of a defect that controls the nucleation phenomena, heterogeneous nucleation. So that makes sense. So as I was saying, that estimation of actual surface area can be done by obtaining this h dash RMS, that is the root mean square thickness gradient or thickness slope. And let us say that if you want to use this relation for obtaining this h dash RMS, one can easily obtain it. So let me just work it out for you. So this is Q1 here and Q2, this is Q cube, this is C of cube is C0 into Q to the power minus 2h minus 2 and dq. So therefore this will be 2 pi, this is Q1, Q2, and this is C0 here, and this is Q to the power 3, so it is minus 2h plus 1 dq, and so therefore this will be 2 pi C0, and this is minus 2h plus 1, right. So it will be minus 2h plus 2, and here it will be q to the power minus 2h plus 2, and limiting values are q1 and q2, and then you can get the final value. So this 2 minus 2h plus 2 is here, so this 2 will get cancelled, and so finally we get relation like that. So you see, having, if you know q1 and q2, what value you would like to use, so that depends upon the range that you are that in the range in which you want to obtain this h dash RMS, okay, and you know this h Hurst exponent, you can obtain okay, this value. So now this a matter, okay, this is a quite a involved subject, okay, this roughness of a surface, how it affects adhesion, and over the years there are several authors who have actually worked on it, on different aspects of it, and different way they have described it. For example, Fuller and Tabor, they described it, the surface as having asperities, right, and then Johnson, he considers a slightly wavy surface, and then let us say Guduru, okay, also considered this elastic wavy surface and basically single wave or something like that. But the surface has got not the single wave, it has got several waves as we just described, and that randomness, or let us say the hierarchical randomness, that needs to be taken into consideration. So you can, so I have actually listed all these references, okay, for someone who is more interested in this topic, and one can read the papers by Professor Parson, for example, and Johnson, of course, JKR, no, Johnson, the same Johnson of JKR contact mechanics. This Johnson's relation that was worked on a little bit more by Popov et al. Who are here, and they there is a Johnson has come out with a Johnson parameter, so that they modify it, okay, in this particular paper. So you can have a look at it. So I will like to today say this thing, the Johnson parameter is given by this expression, and so here you see alpha is a ratio of W as work of adhesion, H is the amplitude of this wave, the variation of the surface. So the surface is considered to be a sinusoidally varying, so H is basically the amplitude of that, let us say, and E star is the modulus. So you see, if E star decreases and W increases, so this Johnson parameter increases. So what it means is that if you have a surface like this and if you have an indenter or an adherent like that, then if the H is small enough, so H is small enough, then this surface, okay, will have the ability or desire or possibility to come in complete contact with this with the adherent over here. So that means this adhesion between these two surfaces, even without any load, okay, P is 0. So at 0 load, we will have the possibility to come in complete contact, okay, when brought sufficiently near, because this material is smooth, this material is soft, this is a soft material, that means modulus is low and the work of adhesion is high. So what it means? So there is a critical value of this alpha, which is called the Johnson parameter, okay, at which the surfaces jump into complete contact even at 0 load. So that was described by Johnson. So very similar to the one, that result that I told you, at the very small range of this amplitude of this surface undulations, roughness, there is increase in adhesion. So once this happens, that the whole thing comes in contact. So in a sense, what happens here is that contact area is actually large, because the surface area here is larger than the nominal surface area. So as a result, the work of adhesion, okay, the effective adhesion, work of adhesion, that can increase. So this was given by Johnson, but you see, Johnson considered only one particular wavelength and having same amplitude. This particular wave has of course only one amplitude, but in a sense, in practice, it will not be one amplitude, several amplitudes are there. It is a randomly rough surface. So that was considered by Person et al, and there are several papers of Person and very elaborate contact mechanics that he does. So I do not have time, or I will not be able to describe all that today in this lecture. This is the last lecture anyway. So here I would like to show that there are some results of Johnson. So Johnson considered, not Johnson, Person considered the energy of the system. So suppose this rubber, which is soft, comes in complete contact with this particular rough surface, which is hard solid, and then what will be the adhesion, what will be the energy of adhesion energy. So adhesion energy, the excess adhesion energy that will be released because of this adhesion will be this quantity. So here you see this quantity is basically the area, the increased area, okay, of this particular surface. So surface nominal area is A0 and this will be larger than that, right, and that is taken care of by this relation. So this is basically the surface energy, which is considered to be proportional to the contact area. And because of this material coming in contact, so there has been some deformation. So that deformation is elastic deformation. So the excess energy that is released because of this adhesion now will get absorbed, okay, by this will go to form this excess elastic energy. So that is taken care of by this relation, okay. Now here this is the relation sigma zz. So that is the stress into area is force, and force into displacement, this is the vertical displacement at the surface, that is energy. So that way it is. So this is the stress into area will be force, and force into distance, that is display deformation, okay, that is the elastic energy, and one obtains the ensemble average of that, right, over the whole area. So that becomes the total elastic energy. So basically these two energies, okay, in a way takes into account that excess part, okay, is this energy, that is the nominal energy, and W means now the actual contact, actual work of adhesion, into A0 is the nominal area. So this relation, so this energy, change in free energies because of this rubber material coming in contact with this rough surface will be given by this. And Person further worked on it, and then by these relations, okay, along with those power spectral density for this self-affine surface, finally give rise to this particular equation of actual work of adhesion divided by the nominal work of adhesion, the whatever it is for the smooth surface, that is capital W. So you see, this is W actual by W, it is equal to 1 plus some quantity. Now this quantity, this whole thing, this will be positive if Q1 is larger than Q2. So what means that if Q1 is larger than Q2, then there will be increase in adhesion, okay. On the other hand, if this quantity Q1 is less than Q2, then of course the actual adhesion decreases. So that is the way it is, and here Q0 is the lower cutoff wave vector, and Q max is the, of course, the higher cutoff, that is the resolution of the AFM tip or whatever is the magnification that you are going for, and then this H0 is determined by the RMS roughness of the surface by this relation. So, these are the definition. E star, of course, we know that is Young's modulus divided by 1 minus sigma square Poisson ratio square, and W is the work of adhesion over here. So, you see this ratio, okay, is dependent on the work of adhesion over here. So, here if this quantity is very high, work of adhesion is very high, let us say, and elastic modulus is soft, then it says that Q2 is small. The Q2 is small, then Q1, then of course adhesion increases, because this surface, okay, this soft surface, that is a soft rubber like material, that will come in contact with this rough surface easily, okay. So, therefore, adhesion will increase. On the other hand, if let us say H0 is large, that is the amplitude, okay, this RMS roughness that is actually large, and then let us say Hurst exponent that is also large, okay. So, now the W is small, let us say, okay. So, that means there are not enough adhesion. Then of course, the actual contact area, so this is the surface, actual contact area will be smaller than the nominal area. So, therefore, this term, the whole thing will be negative, and as a result, okay, this term will be larger than this, Q2 will be larger than Q1, and as a result then the actual work of adhesion will decrease. So, it is a nice way of taking care of this area. Now, there are more other there are several other points, and Parsons has worked on, so I am not going to deal with that. So, what I will like to do today is that I will like to apply this theory for one particular problem which is very important, like particle adhesion. So, particles adhering to a rough surface. So, how exactly do that? So, the surfaces that we have are different. So, I can see that we can actually design different surfaces and having different fractal dimension, and we can estimate the surface roughness by this RMS roughness by considering this whole range of the surface features, okay, from very small to large. For all these cases are characterized, okay, this HRMS is characterized, okay, by considering the surface features over their whole range, and we have this PSD curves. And as you can see, we have here, let us say our HRMS of 1.8 micron, fractal dimension 2.3, here it is 0.8 micron, 2.17, here it is 0.6 micron, 2.03, like that. So, this HRMS or H-RMS, whatever is written here, that is considering the whole range of these features. That means, let us say from very small to large and like that. Now, for a particle, however, situation is something different, because particle, when it comes in contact, okay, it the large scale features, okay, that does not count, because that does not affect this particle adhesion. Particle sees as a smooth surface, as a large wavelength features. It is only the features, okay, diameter when it is smaller than wavelength, okay, smaller than wavelength, diameter is smaller than the wavelength, it is smooth surface it is. When the diameter becomes larger, okay, greater than equal to large, then only particle sees the roughness. So, for example, in this case, okay, particle sees the roughness because these features has the wavelength that is smaller than the diameter of the particle. So, that point is to consider. So, what it means is that it is the surface features having dimension smaller than the particle diameter that will affect, okay, the adhesion. Otherwise, adhesion is the actual work of adhesion is actually equal to the thermodynamic work of adhesion, right. So, if it is a smooth surface, then of course, the thermodynamic work of adhesion that will work. But if there are features or the features having smaller wavelength, that will not affect, that will affect the adhesion, okay. So, surface features with diameter larger than lambda, that actual area of contact differs from the contact between the two surfaces. So, we will consider like that. So, therefore, suppose we have got this particular particle of 10 micron, and then so you have got another particle 0.15 micron. So, although the surface is same 2.11 here, 1.34 over here, so the features of the surface that will affect this adhesion of this larger particle is over this area. However, here as the particle becomes small, so the features of this size, okay, that will all remain, so that will appear as a smooth surface, okay, for this particle. So, it is the features of this range that will be sensed as a rough surface for this particle. So, the roughness is will be like that. So, now we can estimate the RMS roughness above for this range, okay, and RMS roughness for this range, okay, that is the way. So, that is represented by Rp. So, when you use this expression over here and we have to estimate this roughness, this H0 factor over here, H RMS square over here, we have to consider therefore different RMS roughness for these two different particles, or the surface is same. So, surface is same, but the particles are different sizes. So, we have to consider like that. So, doing all that, so we have different value of Rp now, Qp and all that, and now particle, when you calculate the actual work of adhesion, so this Qp will also now be different. This is a lower value cutoff wavelength, because it is the Qp over here for this particle is this value, and that is 0.6 micron inverse, and here Qp is 42 micron inverse. So, this value. So, we have to consider accordingly, and we do all this calculation over here above, okay, as per this equation, right, and then we can do this. So, we can choose that how this work of adhesion will vary for these different cases, and we get this. So, suppose we keep this work of adhesion W constant and the Young's modulus of the surface, okay, that constant, and now we bring this particle in contact, and then what happens is that this different fractal dimensional particle, the actual work of adhesion by W, that will vary something like this, okay. So, work of adhesion will be quite, actual work of adhesion will be quite large for this intermediate sizes, it maximizes, okay, at some range. So, it makes sense because if the particle is very large, then the RMS, then the particle is very large, then the roughness of all different length scales, okay, are sensed by the particle, and if it is very small, then it is basically a smooth surface, that is what it sees. So, intermediate somewhere, okay, the adhesion will be maximum, and here in this plot work of adhesion is being varied. So, here for example, if you have Young's modulus same and you say the RMS roughness remains same, now particles having different work of adhesion. So, if the work of adhesion is large, then of course the actual W actual by W, that will be large, right. But however, if you can decrease the work of adhesion, then of course this value decreases for different particle sizes. So, you see also that this curve is different for the different particle size, in the sense that if you let us say have this this is 60 millijoule per meter square, this circles over here, okay, and now this is the particle 10 micron, and then if you can decrease the work of adhesion to some extent, then this is for 20 millijoule per meter square, so 20 millijoule square somewhere comes over here. So, that means that if you can decrease the work of adhesion to some extent, the particle becomes almost free on the surface, the almost debonds, right. So, that can be done some experiment, we can choose, we can verify that in experiment, and if for details you can look at this particular paper of mine, and we have described this phenomena by using this toner particle. So, that is all for this course. I have come to the end of whatever I wanted to teach in this course, and I will like to take few more minutes of yours for describing the summary of whatever I taught, and here are this. So, I started with introduction, stress equilibrium relations, and then I talked about equilibrium of elastic half space subjected to line and point forces, and then I talked about distributed load. I talked about Hertz mechanics, solid bodies in contact with or without interactions, the introduction to surface energy, surface tension and adhesion force. So, I described quite in detail about how to estimate the interfacial energies and interfacial then work of adhesion and all that, thermodynamic work of adhesion. I also described how to derive this Young's equation using Lagrange multipliers, methods of estimation interference, as I said, JKR contact mechanics I described, contact between two spherical bodies, two cylindrical bodies, and then rolling contact mechanics, and while doing that, while doing all this, I also described what is contact hysteresis. I described rigid punch with convex, concave and the flat head on an elastic half space, and I also described that what is an optimized concave shape, okay, for a punch for maximizing adhesion. So, we described that. Effect of splitting of contact area. So, you have the contact area remains same, but you have several punches, let us say, how that will affect adhesion. Then I described these different models of adhesion, Dugdale model, DMT model and Mojis Dugdale model and all that. So, I described that. Then I described that how to apply these different models, in which ranges, okay, they work, and I described this Mojis Dugdale model, presented those graphs and all that. Then I moved to finding out the adhesion of a thin adhesive film sandwiched between two parallel plates. I described two rigid parallel plates and the adhesion between of this adhesive being sandwiched between two rigid parallel plates, and then I went on to describe the bending of a flexible plate, because then I described the adhesive being sandwiched between a rigid and a flexible plate. So, I had to describe this bending, so I did that. I also discussed the peel experiments, and then I went to discuss the lift-off experiment. So, and variation of this peel experiment is a lift-off experiment, I described that. Then I described about adhesion enhancement, okay, without viscoelastic effects via patterning, physical effects, patterning of the adhesive. So, while doing that, I described this incision pattern adhesive once embedded with microstructures, elastocapillary effect, self-adhesion hysteresis and all that. And then I described this analysis of adhesion of flexible adherent, okay, on adhesive with spatially varying thickness and modulus, and then I also described adhesion of viscoelastic spheres, and finally I touched upon this subject of elastic adhesive on a rough surface. So, thus I come to the end of this course, and thank you all, and I hope you like it. And if there is any question or any concern or any issues, please let me know. You will have my email address and my phone number and all that. Thank you.